The first detection of X-ray emissions from the interstellar object 3I Atlas has recently been announced, thanks to the Extend Soft X-ray Imaging Telescope aboard JAXA's XR-ISM mission for X-ray imaging and spectroscopy. The Extend system comprises an X-ray telescope that focuses incoming X-rays and an X-ray CCD camera designed to detect signals across a broad 38.5 arc-minute field of view. Additionally, the XR-ISM satellite is equipped with the Resolve instrument, which enables high-resolution X-ray spectroscopy. The newly produced X-ray image spans a projected square area of 3 million kilometers on each side, surrounding 3I Atlas, and reveals a faint emission glow that extends as far as 400,000 kilometers from its center. Before this discovery, 3I Atlas had solely been observed in the ultraviolet, visible, infrared, submillimeter, and radio wavelengths. The emission of X-rays from comets in our solar system was first identified in 1996 around Comet Hyakutake and has since been confirmed in other comets, but X-rays from interstellar objects had not been detected before. Given its substantial mass and large coma, Comet 3I Atlas was an ideal candidate for X-ray observations. The XR-ISM satellite conducted an observational window for 3I Atlas 1 month after its peak brightness during perihelion on October 29, 2025, while it was concealed behind the Sun and not observable by Earth-based satellites. XR-ISM is restricted to observing the sky at distances greater than 60 degrees from the Sun, which led to its observations of 3I Atlas being scheduled from 2320 UTC on November 26 to 2038 UTC on November 28, 2025, involving a cumulative exposure time of 17 hours. During this period, 3I Atlas drifted slowly through the constellation Virgo, prompting the satellite's altitude to be adjusted 14 times at 3-hour intervals to keep it positioned near the center of the Extend field of view. A preliminary assessment of the images centered on 3I Atlas revealed a faint glow of X-ray emissions covering an angular scale of 5 arc-minutes, equating to a distance of 400,000 kilometers from 3I Atlas. This observation implies that the prominent X-ray halo is linked to the gas plume surrounding 3I Atlas, which was previously detected by the Spheric Space Observatory and the Webb Space Telescope in August 2025. One possible natural explanation for the detected signal is X-ray emissions originating from the gas plume around 3I Atlas due to its interaction with solar wind. When charged particles from the wind interact with particles from the gas cloud, X-ray emissions occur. Indeed, the Extend spectrum demonstrates excess emissions related to carbon, nitrogen, and oxygen, in addition to the background emissions from the Milky Way and Earth's atmosphere. This finding provides a crucial hint that the observed emission could stem from charge exchange interactions between the gas surrounding 3I Atlas and the solar wind. This groundbreaking detection of X-rays from an interstellar object will undoubtedly inspire further research by various teams. It will be intriguing to investigate whether other characteristics of the X-rays diverge from the expected signatures associated with charge exchange reactions with solar wind. This finding highlights a new layer of complexity in the enigma of 3I Atlas. While the charge exchange hypothesis with solar wind is a plausible natural explanation, it necessitates a significant amount of gas surrounding the object, which contradicts earlier classifications suggesting it was a depleted or dry comet. The identification of carbon, nitrogen, and oxygen in quantities sufficient for detectable X-ray emissions indicates that the object is far more dynamic than conventional classifications would suggest. This further contributes to the expanding mystery surrounding this interstellar visitor. The initial detection of X-rays from an interstellar object marks a significant milestone in the field of astronomy. It not only enriches our understanding of the variety of objects that enter our solar system, but also equips us with a novel tool to examine the composition and behavior of these enigmatic cosmic wanderers. The continuous revelations and distinctive visual structure of 3I Atlas, along with its energetic emissions, keep the inquiries regarding its true nature and origin alive. Below is a list of the physical inconsistencies that render the comet explanation untenable, with further elaboration provided for each item. Intrinsic X-ray emission, a rigid frontal jet, and an anti-tail aligned with the star. A weak coma and tail, with barely perceptible matter, an anomalous metallic composition, an extraordinarily high nickel-to-iron ratio, strongly negative optical polarization, non-gravitational acceleration without sufficient visible cloud, minimal mass loss incompatible with the extensive presence of jets, rotation and elongation signals that do not align with a fractured icy nucleus, repeated orbital coincidences involving close encounters with Mars, Venus, and Jupiter, an unusual pattern of brightness fluctuations and a bluish hue, jets that are columnated over millions of kilometers, energy requirements that conflict with the estimated size of the nucleus. To start, we examine the presence of X-rays from Atlas's location. X-rays are not merely light reflected from our solar system's parent star. They represent intrinsic energy emission. For a comet to generate X-rays consistently, it would need to be expelling vast quantities of gas, which would interact with stellar wind and particles to create such radiation. Absolutely opposite to what we observe with Atlas, which appears to be quite dry and shows minimal activity. Secondly, let's consider the composition. Research suggests a nickel-to-iron ratio around 10.1 in the observed metallic fraction, resembling industrial alloys rather than the typical composition of a cometary nucleus, which is primarily made up of volatiles and refractory materials in different proportions. This chemical signature raises significant concerns. Thirdly, regarding morphology, Atlas features a well-defined antitail and rigid frontal jets that clearly don't match the model of diffuse ejection of volatile materials. Natural jets usually disperse and display similar colors and compositions when emanating from the same source. However, in Atlas, we witness jets with varying tonalities, hinting at heterogeneity that is difficult to reconcile with a uniform icy nucleus. Fourthly, we must address non-gravitational acceleration. Recorded velocity shifts cannot be solely attributed to gravitational effects. In cometary models, non-gravitational accelerations are a result of volatile sublimation, inducing thrust, which necessitates mass loss and a visible debris cloud. In Atlas, however, we have acceleration occurring without any detectable cloud to justify this significant change in trajectory. In other words, the visible mass is insufficient to explain the observed effect. Fifthly, we assess the energy involved. The existence of such extensive and columnated jets would suggest material flows and energy absorption capabilities that far exceed what a nucleus of Atlas's estimated size could handle if it were merely composed of ice. In practical terms, the volume of material and the velocities observed would demand energy sources or propulsion systems that are incompatible with conventional cometary physics. It's important to note that while an isolated point can have alternate explanations, the accumulation of anomalies, X-rays, excess nickel, frontal jets, negative polarization, unexplained acceleration, irregular photometric behavior, and orbital coincidences changes the entire picture. The likelihood that all these phenomena can be attributed to a mix of standard natural causes diminishes rapidly. The convergence of these signals serves as a form of scientific validation. Initially, skeptical scientists are beginning to recognize that the most plausible explanation is now something beyond a conventional comet. This conclusion represents a reasoned response to empirical observations.